there are physiographic criteria for fault recognition. So first, let's go over these, because these physiographic criteria can work for regional scale faults or outcrop scale faults. So in larger scale, we use this type of evidence for to determine if whether there is a faulting or not. In this figure, also let's get this spotlight. Okay, so in this figure, we can see, you can see a block diagram shows a perfect example of faulting and different morphological features at the surface. This is very not in reality. It's maybe in very few places you will see something this perfect. But in any case, when there is a fault plane, first of all, faults will not be this perfect straight lines. Sometimes they are so hard to recognize in the field, depending on the scale. So that's why you need to know this physiographic criteria. So for example, this fault, you can see at the surface, we don't see a rupture. We don't see this actual fault plane or fault plane trace at the surface, because possibly it produced a really big earthquake at some time. And at the time of earthquake, there was a surface rupture. So you could see it at the surface anymore. What's left after that great earthquake and the surface rupture, on both sides of the fault, you can see different morphological features, because during faulting, either one side of fault plane will move up or down, or it will pass other block in one direction. So that's two typical motion along faulting. In this example, we have a dip slip fault because all the motion occurred in the direction of dip. And these arrows indicate direction on each block. So this side of fault is sliding down and this side is pushed up. So there is a footwall uplift on this right side and hanging wall downward drop on the left side. And if you compare this, in this side of the block shows a cross section. If on each layer, resistance to weathering and alteration, these more resistant layers will erode less, and less resistant layers will erode more. Because of that, this ridged kind of corrugated structure will form at the surface. So these ridges and basins will form. So this is typical basin and range topography in the West Coast. If you fly from here to, for example, to West Coast, from plane, you can see this morphological feature really clearly. So these topographic highs are ridges, and topographic lows are basins, and between each two ridges, there is a basin in the West Coast. So the basin and range topography, it is not a product of folding like this. It is actually a product of normal faulting. So each ridge is bounded by two oppositely dipping normal faults on both sides. And basically ridges are uplifted footwalls of normal faults. But here we have similar morphological feature at the surface, similar to basin and range topography, because of the different resistance of different rocks exposed at subsurface. So this fault now brings these two different types of rocks together, and this side of the fault block doesn't show same deformation features because possibly this side is much younger than footwall rocks. What happens during this type of faulting, as left block or hanging wall slides down, it creates some room, some more accommodation space for newly coming sediments. So before the position of this horizontal conglomerate, actually there was a piece of this basement rock in the hanging wall. So it's like you just cut through this basement rock and slide one side downward. Still this piece of basement rock will hang in there in the hanging wall. And on top of this down dropping block will be filled by newly coming sediments, because deposition will be a continuous process in this case. As footwall block gets uplifted, it becomes a source area for this basin on the other side. If this hanging wall moves down and creates a topographic depression, it becomes a basin. As footwall block gets uplifted, it becomes a horst in this example, and that horst or uplifted footwall becomes a source area for sedimentation. As it gets, because it becomes higher topography, as you know, if elevation increases, then weathering processes will also increase, and more rocks will erode, and those rock fragments will depart from source area, and they will end up in a basin. So this is what's happening here. So most likely this conglomerate is sourced from these rocks eroding in the uplifted footwall. In this case, we have much younger rocks in the hanging wall and older rocks in the footwall. And because of this age relationship, different degree of deformation on both sides of fault, and different degree of resistance to weathering, at the surface expression, we can see different morphological features will be exposed. More important than that, these ridges and mountains at the surface, they will be truncated. If there is a fault plane separating these two blocks, like this one, along the fault line, these mountains will be truncated, so they will not be continuous in the trend in the expected direction. Here we have an example from Utah. Here you can see this is the ridge. You can see this really well-developed drainage system, and there's another one on the other side of the region. And in between these two ridges, there is a topographic depression right here. That's the basin between two ridges. And this structure, again, it is not because of folding. This is a result of normal faults in the region, but same topography. And also, if you look at this side, these ridges are extending in this direction. And at this point, there's a major fault, Wasatch Fault, and that fault truncates these mountains, and you cannot follow these mountains on the other side of fault line. You just find a plain, which is completely different lithology. So truncated mountains, ridges, this is a really good evidence for faulting. After you find it, you can look for that fault plane. If you find the fault plane in an outcrop, we can investigate kinematics or in characteristics of the fault. Is it dip slip, strike slip, or is it normal or reverse? So you can study that. Another good evidence is fault scarps and alluvial fans. Fault scarp is the exposed part of the fault, because these fault planes, they are not always exposed at the surface. Like this block diagram, this fault plane is just buried. It is not exposed at the surface. Only during the earthquake, maybe there will be a surface rupture, and that's the only evidence we can find at the surface. But after some time, first of all, if displacement rate is great enough, big enough, then hanging wall will slide maybe a couple 100 feet or tens of feet. In this case, because of that sliding, some portion of footwall block will be exposed along the fault plane. So that exposed part is what we call fault scarp. So fault scarps are really good if you find in the field, because they can contain fault silicon lines and a lot of other kinematic indicators. And you can use measurements from fault scarp. Basically here at fault scarp, first of all, you can measure strike and dip of this fault plane, because now the plane itself is exposed. So silicon line of this is the plane right here, and it's hiding behind this hanging wall on the other side. So this is the plane, and we want to measure strike and dip of this plane in order to record it on our notebook. So you measure this line, this horizontal line contained by the plane, that's the strike. And now you measure dip angle in perpendicular direction to strike, that we record it as fault measurement. And if during this downdrop motion, another thing that happens, if there is a good well-established drainage system, rivers and creeks like this, they will be disconnected. So this surface water network will be also disconnected because of this motion. And what happens? So here we have these rivers flowing in one direction, maybe in this case from west to east, and that river system has its own energy, and then this energy basically is how it is how these rivers can transport and basically carry heavy, pebbles and sand and a lot of rock fragments and help deposition processes. So this river system has some energy, and as it reaches to this point where we have fault scarp, because of this elevation change, the internal energy of the river system will change, and everything will be dumped to on top of hanging wall, and that will be like a delta formation. But this time it is not covered with water. It is just continental environment, but it happens underwater too. So if we can find the same process underwater faults, especially dipsel faults. So in this case, this river system will form this alluvial fans on the surface of hanging wall block because of that energy change between footwall and hanging wall. And these alluvial fans will be very interestingly, they will be just aligned in one direction. They will not be just randomly forming in the region. They will be parallel to a linear feature at the surface, which is the fault trace, fault trace line on the surface. So this fault right here behind this alluvial fans, this is the strike of fault. Again, this is also strike of the fault. So these horizontal lines are defined strike orientation of the fault plane. And these alluvial fans will be parallel to strike of the fault in the region. So I'll show some examples in the next slide. Actually, let me show. So this one here, for example, right here we have a truncated mountain, and then there is a plain. So this is the hanging wall block, and this is the footwall, which is getting uplifted. And between this uplifted footwall and down dropping hanging wall, this river transports lots of fine sediments in this direction. And when it comes to fault line, it is basically dumping everything on top of hanging wall and forming this big, beautiful alluvial fan on the hanging wall. There was one more figure. So here you can see so alluvial fans are following fault line. Even here, these in this direction, and this is just one of them. And also at the surface here, you can maybe notice this very planar surface. It's like as if someone cut with knife. It is not. It is just a plane, defining a plane, which is the fault scarp. So we'll come back to these figures. Before that, one interesting thing you need to know, because it can be really confusing when you study with faults. Sometimes because of the different strength profile of rocks forming fault blocks, what is exposed at the surface or fault scarp exposed at the surface can be misleading in terms of when you want to determine sense of slip. In this block diagram, this is explained. So here we have this fault plane, and we know that this hanging wall is sliding down in this direction and footwall is getting uplifted. And after this uplift, footwall block, some part of footwall block will be exposed. So this is the fault scarp. And based on this configuration, we can compare marker layers on each side, and whichever side is down dropping, it helps us figure out if it's normal or reverse fault. Because this hanging wall is dropping down, it's a normal fault. And in the next step, this is what could happen if we have more softer rocks in the footwall and more resistant, harder rocks in the hanging wall. After fault scarp formation, the softer footwall rocks can erode faster. And because of this faster erosion rates, these footwall rocks can be gone, and hanging wall rocks can still resist erosion, and they can make this kind of pseudo footwall image. So in this case, if you find this outcrop in the field, because usually this is the case, we find the last scene of the movie. So if you find this outcrop, it can be very misleading because it looks like this side is uplifted. But but we know that this side is not uplifted. It is actually a normal fault. This side was sliding down. Other part of the fault plane was actually getting uplifted. So what happened, this uplifted block was softer rocks. In composition, it had more maybe softer rocks, and it was eroding away much faster than hanging wall. That's the reason now we don't have this uplifted block at the expected, elevation in the region. So we have to always be careful when we study with faults. Don't make conclusions right away just by looking at these geometries in the field. Always find the fault plane first and find marker layers on each side, and then determine if it's a normal or reverse fault. Then you can understand why we have this block, hanging wall block, at much higher elevations in the region. And that answer is different erosion rates. So going back to these figures from California, Death Valley. Death Valley is a beautiful place to observe faults, normal faults, and structural faults. You can see these type of alluvial fans. You can see one of them is here. So this is one alluvial fan. And there's another one here, and there's another one here. So here on this photo, you can see 3 alluvial fans, all parallel along the fault plane. So there is a fault line going just at the tip of these triangles. So that's the fault plane, and all of the alluvial fans are basically forming from that fault line, and they grow out in the opposite direction, which is down dropping direction. And this one is also, I just explained, this is another example. So you can see this kind of dip in this direction. This plane is dipping to the southwest of the photo, and this alluvial fan is just spreading out on the top of hanging wall. So triangular faces, these are another good evidence, especially around Sierra Nevada. These are so obvious, structures. When you drive by highway, you can see a lot of triangular faces on the surface of the road cut. These structures also form as a result of erosion. So when fault plane forms, this fault scarp will be exposed, and after, especially when footwall block gets uplifted, a good drainage system will start, and that drainage system will carve down into footwall, and that carved surfaces will form this kind of disconnected triangular faces in the front side of the footwall. So at the end of this erosional process, this is how it will look like. So this is the first stage, as these rivers carved down into footwall, and at the same time, this material during the carving will be transported by the rivers, and it will form an alluvial fan at some point. And as these rivers carve more into this footwall, these alluvial fans will grow up, and then and they will be wider, and at some point they will be connected like this. And what will be left after erosion is alluvial fans in the hanging wall, and this triangular facet exposed along the fault scarp on footwall block. So this is a field photo from West Coast again. So you can clearly see this triangular structures. It's from West Coast, from Sierra Nevada. Water accumulation, that's another interesting thing that happens during faulting, especially for some special type of faults like detachment faults, low angle normal faults. A lot of fluids will involve in the deformation. So this fault plane will be like a conduit, and a lot of fluids will just will be coming from deeper layers to surface, or even atmospheric water will just come from surface, and it will be filtered to down lower layers. So these water cycle along the fault plane, sometimes it's responsible for precipitation of really economically valuable minerals, like gold and silver precipitation in Nevada, for example. It's mostly controlled by faults in the region. So water accumulation can be this way. So that water can basically, faults can affect, first of all, groundwater system, and that can create uh, some um, some kind of migration of water from deeper layers to surface, or it can be also infiltration of surface water into deeper layers that will change rock strength at deeper layers. But in this slide, we show how this surface water accumulation or water bodies form at the time of faulting, during faulting processes. So this is one way is if there's a river system in the region, after this river system gets disconnected by a dip slope fault like this, and on the hanging wall, not only alluvial fans, but also small local lakes will form. So this disconnected river will dump lots of water on the hanging wall, and that will create a lake, especially if you have impermeable layers on the other side of a fault line. It will be creating this type of local lakes. And after, if water supply cuts by another faulting process, these local lakes or small lakes can dry out, and they can also form swamps. So you can find swamps and lakes, again, like parallel to fault strike line in a region. Then it's a good evidence that there's a big major fault forming these local lakes aligned in one direction, or forming swamps aligned in one direction. If it's dip slope fault, this is the most likely this is the case. If there is a strike slope tectonic, then you can also find another evidence just by looking at the geometry of water bodies in the region. You can basically estimate where is possibly there's major fault. In this figure, for example, we have tilted fault block mountains on one side, and on the other side we have another block of the fault. And here, these lakes forming because of this process, down-dropping block is sliding down in this direction to northeast. And as this river system cuts by fault, these local lakes will form. And sometimes these lakes can be connected and form much larger water bodies at the surface. Another thing, when there's a strike slope tectonic, if this line is not a normal fault but strike slope fault, these lakes can be stretched and elongated in one direction. Instead of forming a circular lake, they can form this stretched, elongated, more linear lakes and lagoons or swamps at the surface. So that indicates there is most likely a strike slip fault running parallel to the alignment of lakes and swamps in the region. So this is an example from West Coast. Here, San Andreas Fault is just going in this direction. It's a right lateral major fault. It's a transform fault, separates North American plate from Pacific plate. And as it extends in this direction, and these two sides of block pass each other, as you can see, this lake is extended parallel to the motion along San Andreas Fault. And there's another one here, Imperial Fault. Because these two faults have same sense of slip, both faults are right lateral. This is what will happen as this side of the fault balloon moves left, and this side of the same block moves right. This block will be wrenched in between two strike slip faults with the same sense of slip. So we call this wrench tectonics, or wrenching. So that's another process. Offset stream channels, that's really great evidence, really good evidence. Sometimes it's better visible if you have aerial photos, or if you have a chance to fly over area. A lot of mining companies actually do that. They just fly a plane and for paleomagnetic and some geophysical measurements. At the same time, they take this type of aerial photos and observe faults. So this is one good evidence. Here we have a river system. You can see this one branch of the river is going in this direction. Another branch is going in this direction. Right here at this, when we come to this white line, This is the actual surface expression of San Andreas Fault. So in this direction, we have San Andreas Fault. It's a right lateral fault. So this side is moving right, and this side is moving left. And you can see this this river changes, direction um, to the left right here. This curve to the left is basically because of this left motion. And on the other side, it is cut by San Andreas Fault right here. So there's offset on the stream channel. And on the other side, same river system, basically making a jump. So from this point to this point, it's jumping from this point to this point, and there's a disconnection right here. So it starts from here again and continues in the same direction. Because this river was already here before San Andreas Fault extended in this direction, and because of that, now you can observe this offset after lots of kind of recent active tectonics in the region. Active faulting and morphology, it will definitely affect geomorphology at the surface. Here you can see this is the highway going in this direction, and you can see this uplift. This is the fault plane, by the way. Here in this direction, we have a fault plane, and this is the uplifted portion of the fault. This is footwall, and this is hanging wall moving down in this direction. As a result of that, you can see this geomorphological feature is changed by a faulting process. So for example, in the topographic maps, now we need to add one more contour line on the other side, because elevation at this point, right, if depending on the scale, if we can make some numbers, if we are at, let's say, 100 feet here, and then on the other side, it will be maybe 120 feet or 110 feet, which adds contour lines on the topographic map on one side. And okay, we still have time. So on the map, how can you recognize faults on a geologic map, or on a well log, or on a seismic profile? So on two dimension. So here we have an example of a geologic column, shows geochronological order of units. So we have youngest unit, this light blue is sandstone is oldest, and this kind of yellow color sandstone is youngest, and in between we have other formations. We have 10 units. And if you look at this geologic map, each unit is mapped out and numbered based on the formation names as numbers on the column. Here we have oldest unit, and then younger and relatively more younger unit, number 3. So until this point, everything looks okay because everything in order. And after this point, we have this older unit exposed again in the same unit. So after the position of 1 and the position of 2 on top of that, and the position of number 3 on top of other 2, there is no way we can add more number 1 on top of 3, because the position of number 1 is done, and then it's covered by number 2 and 3. So on the way, there's only one way to find exactly the same older unit repeated and is in the field. It can be faulting. So there should be some kind of brittle deformation. In this case, it's a fault. Bring this older unit back to surface again. So if you look at the cross section of this map, right here we have number 1 exposed. This is number 1 oldest unit. And here we have number 2. That's the orientation of number 2. It is dipping to the east. And on top of number 2, we have number 3. And on the other side of this line, we have number 1, oldest unit, pops up at the surface because of this normal fault. As this normal fault formed between number 3 and 1, this side footwall will be uplifted, and during the uplift, this older unit will be pushed up in this direction, and younger units will be also pushed up in the same direction. And after erosion of these top younger units, this older unit will be exposed at the surface through a window. So right here we have oldest unit exposed in the footwall of a normal fault. And on the other side, we have younger units exposed. So this is a typical relationship, age relationship for normal faulting. When normal faults form, hanging wall block will drop down and create more room for deposition of younger units. Also, this down drop motion will push hanging wall down, and it will basically push older units to deeper levels. So depth of older units will change, and they will be found at much deeper levels. And younger units will be also pushed down, and they will be found at deeper levels. But in any case, you will find younger units above older units. If you just pick a point along the fault line, look at both sides of that line, that point. On the left side, which is above fault line, because fault line is tilted like this, it's inclined to the west. So this is the above, and this is below fault line. So above this fault line, here at this point we have number 2, and at the same depth we have number 1 below the fault line. So younger units will be always on top of older units if it's a normal fault. So that's a typical age relationship for normal fault. Younger on top older. And then let's continue with map. Here we have number 1. And also you can see these formation contacts correspond to boundaries between between 2 formations on the cross section. So we are making a slice in this direction. And after 1, 2, and 3, interestingly, we have number 8 exposed, which is way younger than number 1, 2, and 3. And also another important thing, when you look at the column, between 8 and 3, we are missing some units. So unit 4, 5, 6, 7, these are all missing, and they are not exposed in the field. So let's see what happened to those units. So here, we have a reverse fault. So this reverse fault also inclined, tilted to the west like normal fault, but this time hanging wall block, which is the block above fault line, it is not sliding down, it is actually pushed upward. It is moving upward as a result of horizontal sigma 1. So this block moves up. In this case, these deeply seated older rocks will be pushed upward, and they will come to shallower depths, in this case, along the fault plane. And this is what's happening. Number 1, it was pushed down by normal fault on this side. Now it's pushed upward by reverse fault and coming closer to surface because of this reverse sense of slip along this line. And also, this hanging wall block, normal fault also push footwall up. So collectively, this footwall uplift and hanging wall upward motion brings number 1 closer to surface. On the other side, in opposite of normal fault, this footwall block now will be relatively moving down if you compare motion to hanging wall, because hanging wall is upward and footwall will be moving down in this direction. So it will push older units deeper in this direction, and much younger units will be exposed along the traverse. Because of that, now if you pick a point along the fault line and observe which units do you have on both sides of this point. Here we have number 2, which is way older than other units. And on the other side, we have number 7 and 8. So we have older units on top of younger units. So that's typical age relationship for compressional faults. Reverse faults or truss faults will always display older units on top of younger units. An easy way, like I said, pick a point along the fault line, and at the same depth or elevation, look at the both sides of fault line. If you have older units on top of younger units, then you have a reverse or truss fault. Difference between reverse and truss fault is dip angle. This is a reverse fault because it's still moderately dipping. If you have a fault plane with exactly the same type of motion and sense of slip, but at much shallower depths, less than 30 degrees, that's a thrust fault. So this is how you can find faults in just by looking at map. If you have formations missing on the map in the direction of dip, for example, then that's a good evidence that there is most likely a fault plane. It can be also unconformity. So you need to go back and check if there is any evidence, any additional evidence for faulting. But this is what faults will do, and they will definitely, in some regions, it is these faults are messing up stratigraphy so bad, it can be really confusing. I remember in one project we spent almost a month just to figure out stratigraphy because faults were basically chopping out everything in such a small pieces. It was so hard to put things back in order and find stratigraphic column. So it can happen. It can make geology much complicated. That's why you need to know how to recognize faults in the field, and on top of that, how to determine sense of slip. They are not just messing up with maps or field exposures, but also I believe a lot of people from this class will be dealing with this type of problems in the future because you will be working with well logs, seismic profiles, and you will see lots of faults, especially at subsurface images. They are really well exposed and preserved. You will find more examples of these problems in subsurface images. So in this type of well logs or seismics, you will see stratigraphic separation. Similar to this previous image cross-section, some formations will be missing, so omission of formations is one problem, and some formations will be repeated. So that repetition of the units will be basically because of reverse faults or thrust faults. So here we have a missing section right here. After you drill through these rocks, you get a full core from A and full core from B, and full core comes out from D and E. And for some reason, in well location C, you don't recover all of the stratigraphic column. So some part of column is missing. So the big question, why this happened, is it related to drilling or is there something like tectonic feature? So if you look at the cross section, this is one possible answer to that question. If there is a normal fault like this, that normal fault will push hanging wall block down, and because of that down drop on the hanging wall block, this layer, for example, let's say this is our marker layer. So this marker layer will be drilled at much greater depth. So first of all, drilling depth will change. So if you drill this marker layer, if it's maybe a good reservoir, or maybe this is a layer with lots of high-grade gold. So in this case, you want to know what's the depth of this formation, what will be drilling depth. So in the hanging wall, in the footwall, because footwall will be uplifted, you will be able to find maybe these layers at much shallower depth. And in the hanging wall, they will be pushed down in this direction, and maybe drilling depth will increase. If there is no fault scarp like this, if you fill this portion with more rocks, now you can see how drilling depth will increase in the hanging wall because of the down drop motion. So another thing, because of the offset displacement by fault plane, that will be separation of units. In this case, this is dip separation. In the direction of dip, these formations are separated. And because of the stratigraphic separation in the direction of dip, you will not be able to find this formation exposed in well C. And it will be just missing some part of stratigraphy. Another way, if in some well logs or borehole images, you can also see same marker layer repeats more than once. And one possible reason for that, if you have this kind of inclined drilling, maybe you drill through same marker layer 2 times, and you will find same formation 2 times in the well log. So that's another possible reason for repetition of units. But if it's tectonic feature related, most likely there is a normal fault like this, and that caused omitted stratigraphic. If it's a reverse fault, this formation will be repeated, and that will be repeated